In this video, we're going to learn about another piece of the momentum puzzle, and that's impulse. Impulse, as it turns out, is just a fancy name for a change in momentum. So some books use a capital I for this. I don't even bother because an impulse is just a delta P. So an impulse is not something that an object has, but rather something that an object experiences. So if a rocket ship has its engine and it turns it on full blast, that delivers an impulse to the rest of the ship. It is changing its momentum, causing it to accelerate because there are forces. This is related to other things we've talked about, as we'll see in a little bit. So I just use delta P for my impulse variable, and it is literally the change in the momentum of an object from something acting on the object. And that could be something external hitting your object, for example, or in the case of a rocket ship, something changing its own momentum in some way. Okay, so let's do just a little quick derivation to show us how this impulse business works. So if our momentum is equal to mv, our impulse, delta p, so if there's a change in the momentum of an object, that is not because the mass of that object spontaneously changes, that is because the velocity of that object changes. So an impulse here is happening because of a change in velocity of our object. And this change in velocity presumably happens over some amount of time, right? If an object experiences an impulse, it has some initial velocity, it has some final velocity, and it took some time to get between those two things. So what I'm going to do here is I'm going to multiply this by that time, delta t, divided by itself, right? So this is just equal to 1. So I have delta p equals m delta v times delta t over delta t. So this is just 1. So I haven't changed my equation by multiplying by this. But here's what I'm going to do. So m, I'm going to move one of these delta t's underneath this delta v. And now note what I have here is m times delta v over delta t. This is our average acceleration, right? Delta v over delta t is our average acceleration. If our acceleration is constant, this is our acceleration. But even if our acceleration could be changing, this is still our average acceleration. So the mass of our object times the average acceleration, that is equal to the net force, or if we're being really careful, the average net force on the object. And we still have this delta t here. So this impulse equation gives us a connection between the change in the momentum of an object and the force that that object feels. So anytime we have a net force on an object that's exerted for some period of time, we will have a change in momentum. That object will experience an impulse from that. All right, let's do a little example of this. I think this is a good example. So impulse calculations are often done to figure out how large forces are, and so we'll do the example and then we'll talk about it. Okay, so let's say we have a ball thrown at a bat. So here's our bat, and we have a ball going towards it. The ball is 150 grams and is moving at a velocity of 30 meters per second. Okay, so some amount of time later, our bat is hitting the ball. There's some force happening here. We don't know the details. And then some amount of time later, our ball is now going off to the right, and we'll say it is traveling at 80 meters per second. So significantly faster than it was when it was thrown. So the ball's thrown this way, the bat hits it so that the ball gets hit off that way. So the ball changes its direction here from left to right. Okay, so here's the question. If the ball contacts the bat for 2 milliseconds, that is 0.002 of a second, what is the average force on the ball? What is the average force that the ball is experiencing from the bat? Okay, so we can treat this as a momentum impulse problem. So this is where we want to know, how hard of a force is the bat exerting on the ball. So let's look at our momentum before and after. So for this, our system is just the ball. We don't know anything about the bat. We don't know its mass. We don't know its velocity. None of that matters because our impulse equation is just for that single object. We don't have to worry about a system of things for our impulse. Okay, so our momentum here, mv, so our mass is 0.15 kilograms times our velocity, 30 meters per second, but this is momentum. It has a direction. Our momentum is to the left, so this is minus 30. That is important. So 0.15 times minus 30 is minus 4.5 kilogram meters per second. All right. Over here, our momentum is mv, that's 0.15 times 80, which is 12 kilogram meters per second. So delta P, and this is where when I do this problem, asking students about it, where one common mistake is delta P. They want to say 12 minus 4.5 is 7.5, but that's not right? The difference between these 12 and minus 4.5 is 12 minus 4.5, which is 16.5 kilogram meters per second. So the fact that this ball changes direction makes this impulse even bigger than it would be if the ball was going 30 meters per second and then got hit from behind so that it sped up to 80 meters per second or something like that. Okay, so delta P is 16.5 kilogram meters per second. Okay, so our impulse equation, remember, is delta P is equal to F delta T, where this is the average net force, that is the force that we're interested in. So to solve for that, F is equal to delta P over delta T. So that is our 16.5 kilogram meters per second divided by our 2 milliseconds. So that's 0.002 seconds. So solving this, we get our force is equal to 8,250 newtons. Average. So over the process of this hit, sometimes the force is a little higher, sometimes the force is a little lower. 8,000 newtons is really big. So that is the weight of something that has a mass of 800 kilograms, which is 1,700 pounds. So this is the weight of a very small car, but still a car between the bat and the ball. So this is this is a lot of force happening over a small period of time. So anyway, I think this is kind of a cool calculation. You can use similar sorts of things for other other objects hitting other things and see also how big those forces are. I don't know. It's kind of cool to see the scale of some of the forces involved with these sorts of everyday things. So yeah, this is a pretty typical impulse example. We're usually solving for the force in this sort of situation, or we could also, if we knew how big the force was, we could also use this to figure out the time that these two things are interacting with each other. So that's another thing you could solve with this problem.